Hi, everybody. Can we do a quick sound check to the audience and just say or ask a question in the chat window if you can hear me? Again, can somebody in the audience just verify they can hear us in the questions tab, please? All right, let me do a quick sound check with the audience. Great. Okay, I'm getting confirmation that everybody could hear, so we'll start our webinar. Well, good morning, good afternoon, and good evening, everybody. My name is Ian Gomez, and I'm the Community Manager at H2O. Thanks for joining our How to Approach a Multi-Class Classification Problem Using H2O webinar today. Leading the discussion is Ashrith Barthur. He's our security scientist at H2O. Ashrith is working on algorithms that detect anomalous behavior in user activities, network traffic, attacks, financial fraud, and global money movement. He has a PhD from Purdue University in the field of information security, specialized in anomalous behavior and DNS protocol. So here are some logistics regarding the webinar. Please submit your questions throughout the session. You can submit your questions via the questions tab in your console as you did, and we'll be happy to answer them. Also, the webinar is being recorded. A copy of the webinar and the slides will be available after the presentation is over. So without further ado, I will hand it over to Ashrith. Ashrith?
Thanks, Ian. I'm guessing everybody can hear me, just checking from my end as well. Anyone who cannot? And Ian, I'm guessing you can see my screen as well?
Yes, I can see your screen. There's a few people that are having audio issues.
Sure, we can wait till we help them out. Can you guys, like send a chat message or in the question panel to see what the issue might be? We will try to help you out.
They may need probably another minute to join or connect to the audio. So we'll give everybody one more minute until we fully jump into the webinar so you can join, because I'm seeing a few that's not being able to hear. So 1 minute.
Okay, I can see quite a lot of ASs.
Great. We could just jump
yes.
right in. Like,
Yeah. Okay.
Okay, go ahead.
Be fair. So, Ian, we good to go?
Yeah, let's do it.
Okay. Hi, guys. Good morning, good evening, and of course, good afternoon and good night for people in certain locations. Ashrith, and as Ian introduced me, I work as a security scientist at H2O. My primary area of research is anomalous behavior. I design algorithms that basically detect anomalous behavioral, markers in the field of network security and financial fraud. The use case that we'll be talking about today is a very simple use case, which is about classifying. It's basically a multi-class problem where we'll be using a log dataset to classify different logs into certain groups based off the sources they come from. And we'll be using H2O for this. I did have a gentleman asked me a question on the meetup group saying, would I be using Flow for this, or would I be using another, R or the Python API? I'll be using Flow for this because I assume that there might be a lot of people who are new to H2O. In the following talks, we'll actually talk about how to use the APIs. Which is why I have deliberately kept this simple and usable from Flow. So having said that, A quick introduction as to what we'll be speaking about today. So I'll take you through the uh, general introduction of H2O as a company itself. And then a short description about the architecture of H2O, and then the agenda of today's problem that we'll be working with. You know, a bit of definition around the problem. How do we set up the H2O? I'll actually show you like a hands-on thing. And we'll do a wee bit of data analysis, and then we'll get to the results. Now, the thing is, this entire presentation, which includes the PDF that I'm using right now to show you guys, and the code and the sample data set is actually published on our GitHub. And we shall share that with you right after the session. So if you can just bear with us until we finish the session, we would like to share it with you guys so that you can go ahead and try it on your own and experience what we are actually talking about. And in the interest of maximization of time, if you can list out your questions, or if you can keep the questions till I'm almost done, that would be great. But if you have a burning question, you're more than welcome to pop it in the window, and I'll try to answer it as we go along. So as I say again, there are no set rules about when you ask us questions. It would be great if you can keep it to the end. If not, it's perfectly fine. So having said that, so H2O is basically a company that was founded in 2012, a team of 80 people. And much of the folks are actually from Stanford Math, engineers and scientists, and quite a lot of them actually come from Purdue as well. I think that basically is a typo. We should have fixed that. So, the platform itself is actually, a leader in machine learning and deep learning as well. It's extremely easy to use, and we'll see why. And you can interact with the platform using R, Python, Spark. You can run the platform on Hadoop and Spark as well. The platform is open source, so I did see quite a few questions which says that is the platform free to use? Yes, it is clearly free to use. It is open source, so for you to go play around, use it. You do not have to pay us anything. You can even put things into production, and you do not have to pay us anything. Our very fundamental principles are open source, so we live by that. So we believe in contributing to the fraternity. So this is a general talk about our executive team. You can the same thing is visible on our website too, so I won't keep this on for much. These three professors are actually from Stanford, and they've been our core advisory team: Trevor Hasty, Tip Shirani, and Stephen Boyd. I think most of you who are interested in the field of machine learning might have looked at Tip Shirani's and Hasty's book. That is very popular. It's actually freely available online as well. And so, quick introduction to the platform itself. So H2O is basically an open source in-memory prediction engine, which runs on a distributed cluster. So it's parallelized. It makes robust use of the multi-threaded systems. It makes robust use of the clusters and the distributed platform. We have multiple algorithms. We have GLMs, random forests, GBAs, PCAs, deep learnings. We recently also have developed something called as deep learning, which works with other packages like Caffe, TensorFlow, MXNet, etc. We have APIs from different, for different languages, like for R, Python, and those are the main things. And we primarily believe that these APIs are important because most of the analysts use R or Python to do data science. And currently, I think Python is picking up a bit more, so we've got support for this as well. We use a lot of big data. I mean, our platform is primarily developed for big data, which where you can load in hundreds of GB of data, and the platform helps you run your analysis on top of it. So I think most of you are aware of the fact that the field is very broadly divided into supervised and unsupervised learning. And under the supervised process, we have different groups of algorithms themselves. In the statistical analysis, we have GLMs, which is the generalized linear models, with different kinds of distributions. We have the naive Bayes. In the ensemble, we have the random forest, and the version that we have is actually called the distributed random forest. We were one of the we were actually still the first. We were actually the first platform to implement distributed random forest, where we can use all the cores to the fullest to run the random forest algorithm. We also have gradient boosted machines. In the deep neural networks, we have our own implementation of deep learning. And in the unsupervised approach, we have k-means under the clustering. We have PCA, which is a dimensionality reduction approach, and we have autoencoders. For people who are looking at this for the first time, a supervised learning approach basically means that your end target is actually predefined, in the sense your machine knows where it needs to get to. And in the unsupervised learning process, your machine does not necessarily know where it needs to get to. The way it clusters or it groups data is by certain similarity scores or by certain similarities in features. And that's the basic difference between supervised and unsupervised. I won't go much into this because that's not necessarily the focus of our talk today. The way our platform is actually designed is, you can see that there is, the process is completely parallel and distributed. We have the way the data is stored is in memory, and it's a columnar compressed data set. We use special methods in which through which we compress enumerated data or categorical data, or for people who use R, factors. So we also have different kinds of algorithms that we have in the framework. Flow is our most popular way to interact with the model. It is very quick and very easy to pick up H2O to use. So Flow kind of gives you sets a very low bar for you to learn H2O, and within a matter of 2 weeks, you tend to jump from Flow to an API. A certain quick side story to the fact is that when I joined, I had no idea about how to interact through the API, because I come from network security and old school statistics. I started off with Flow. It took me probably about like 7 days of, just about a week, or maybe just under 2 weeks, to learn the whole process through Flow, and then I was jumping into our API very quickly. So that's something for people who are interested in working with it. So one of the first things that that works with H2O is, of course, you import your data. The data can be imported through Flow or R or Python in this case. Actually, before I get into this, I have a quick question to the audience. I do see quite a lot of people saying that they're not able to hear. Could you guys, people who cannot hear me, can you text us and let us know that you cannot hear us? Maybe we can figure out if it's an individual problem, or if a lot of people are not able to hear us. Thanks, guys. I think I'm able to hear a lot of people. I'm able to actually get messages from a lot of people who say they can hear us. Maybe I think. Okay, let's see this. Let's see. Okay, great. I'm getting messages from a lot of people saying that they can hear us. Um, okay, let me continue then. So one of the basic things about H2O, I mean, in any analytical algorithm, is that you need to be able to import data in. Now, if you guys recall, probably a couple of minutes ago, I said that H2O could handle up close to about 100 gigs of data. Um, and for anyone who's tried to, upload documents on a web page or done anything of that kind, they would know that importing 100 gigs of data through a web interface might be really harsh. So you might be thinking, how does that happen? So what we do is our APIs, which is Python, R, and to a certain extent Flow, all talk through the REST API to the H2O core. So what I'm showing right now is how the H2O core with the cloud actually sits. So now let us assume that your data, that you have instantiated an H2O cluster. So let's say there are three different machines here on which H2O running, and there is an H2O cluster. Now, let's say you are sitting here. This could be an R API or a Python. This is your REST API, and this could be an R interface or Python interface or Flow interface through which you're interacting to this H2O cluster. Now, when you say import my data, what H2O actually does is the cluster directly talks to the source of data. There are times I would like to tell you that there are times when you would want to upload data directly from this computer. That is possible too. But much of the times when you have really large data, the data tends to exist on an HDFS, which kind of makes it really easy for the H2O to, take it in. Now, what you actually get here is you basically get a pointer to the data, distributed data set out here. So you're not necessarily moving the data from here into the cluster. You're just getting a pointer. Now, for people who work with R and who work with Python might be thinking that the data set actually resides, in their Python or R session. No, it actually doesn't. So in R, when you load the H2O library, what is happening is the H2O library is basically using the same pointer to the data set to do any kind of transformations. For example, if you were to say drop a column or something, if you were to ask the Python R interface to drop a column, this REST API would basically say drop a column to the cluster, and then it would return back the pointer. It's as simple as that. Now, for someone who who's actually familiar with rows and columns, through R or through Python, H2O uses a similar approach to assemble data. H2O2 uses a data frame. So the data is established in the cluster as a data frame. So through R or through Python, you can talk to the same data frame and do the same kind of transformations. So that's kind of one easy thing that you can do. Now, another important information about the cluster is that the cluster is basically kind of transparent to all the interfaces. So now you could be talking to this cluster through an R interface. You could be talking to the cluster through a Python interface. You could also be talking through a cluster through a Flow interface, all at the same time. And you could probably do bits and pieces of work using each of these interfaces on the same data set. So that's some basic idea of it. So this is how your H2O data frame sits, and the data frame is actually divided amongst your different systems. The data frame is actually divided amongst the different systems, so you have a different set of rows. There's certain grouping that happens, and they get to sit on different machines. Now, having given the basic idea of the H2O architecture, let us try and understand how we can what is the problem we are looking at today. So what we're looking at is basically a large pool of system logs. Okay, so I'm sure all of you are aware about system logs, like sys logs, logs that come from WinSyslog or from your networks and stuff like that. Now, in large organizations, these logs are enormous, and it's very troubling to group these logs. So basically, the problem is logs are very important for organizations because they help debug problems, they help identify security issues, they help trace back people who are attacking, things like that. And one of the things that, which is why organizations tend to have a huge amount of logs. Now, well, there were times when storage was very expensive, so organizations could not store a lot of logs. But now storage is so cheap that these logs are never deleted. You never delete a log, which is very common. And because logs never get deleted, there are lots of legacy logs that are also present in your system, and that causes a bigger problem. It causes an issue when you're trying to identify what logs you're trying to look at. And so let's say you're looking at your house network. In your house, you're looking at your computer, your syslog, your kernel log, for that matter. You are also probably looking at your network logs. So you have like 3 different logs. But organizations usually tend to have like 50 or 60 or close to hundreds of different sources from where logs come, and they need to be able to identify them clearly and uniquely. And that is the problem that we'll actually try to deal with today using H2O. So if we are able to do this, then the advantage for the organization is that it can use this information for analysis, for security, compliance, and create business value out of it as well. For example, Splunk is such a is so well developed that it is able to identify different sources of logs, and it's able to understand how these logs work, which is actually truly building value for a business. So this is actually a sample log data that you have here. Okay, so if in this, what usually happens is you have something like this, which is, sorry for the screen. You have the source of your data. This is a certain source identifier of your log. This is your date and time of your log, and this is the IP address. This is a service that the log is generated, and this is the output of the log. What has happened. In this case, it simply says there's a balance pool, and the next log is actually coming from a different source. It has a different timestamp, it has a different machine ID, it has a different process, and such. Now, if you look at many of these logs, here I'm showing you an example merely. You have quite a few IP addresses. You have quite a few MAC addresses. You have a proc ID. You have a certain date and timestamp, and you have a certain source of your log as well. Now, these are interesting things that you want to look at, because remember, these are key for you to identify your logs. Now, what you do is, after Now, one of the basic things that you have to do is, after you look at this log, you form it into features. So each of these logs, for example, this first log comes from DHCP, comes from a DHCP server. The next log is actually coming from a VMware server, and the following actually is coming again from a DHCP server. So now what we need to do is we need to be able to smartly identify that a certain log is coming from DHCP or a certain log is coming from a VMware server and such. But I, as a person, could sit and look at all these logs all day long and tag them manually, or we could make a machine learn to do these things for us. But for a machine to, for a machine to learn these things, you need to tell the machine what it needs to learn. And when you say that, you are looking at a certain. So when you say what are the kind of things that a machine can learn, there are certain. That is what we call as features. So for example, let's go back here. These logs have a date and time, right? So there is a certain format that these date and time exists. So if you see the first one, it is in the format of month, which is 3 letters, and then there is a date, and then you have the hour of the day, the minute of the day, and the second. And following which you have a more a Unix time, sorry, not a Unix time, a computer representation of timing is how you would classify this one. And you would again, see a similar representation which exists already. So now what's happening is each of these timestamps can actually be tagged as a different kind of timestamp. That's one feature. Now there are different IP addresses in your data set. Okay. Now the different IP addresses in your data set actually exist. So for example, in this log you have IP addresses that are sitting out here, and you also have MAC addresses. So you have MAC addresses as you've tagged out here. Now, sorry about that. And then you also have different sizes of these logs, which is basically some of them are really long while some of them are really small. And so this is another feature that you can use to identify logs as well. And then you have the priority value, which is how you identify each of these logs. So that priority value happens to be this number, 30 or 166, which is enclosed in a greater than and a lesser than sign. Now, this also tells us from the source of this data. Where is this data coming from? Which is very helpful. So, using these these guideposts, these feature designs, we actually go ahead and build features for the data. These features are priority value, which is an actual feature. Then we have the format of the date, which is another feature, and then we have number of characters, the feature, number of IP addresses, number of MAC addresses, and the last one is fraction of dictionary words by size. Now, what does this actually mean? So let me just go back to the data very quickly, okay? And I can show you what I mean, the sample data set. So, by the way, for people who probably are thinking, where is the H2O? I will just come to that. What I'm trying to do here is I'm trying to give you a basic understanding of what the data is and how you look at the data, so that when I actually show you how to bring in the data and run with it, you will know what you're doing. So it's as simple as that. Okay. So please bear with me and do not think I've derailed your whole idea of to learn H2O. So what you see here is you see in the logs there are certain words that come out of the English language, which is like balanced, pool, and then you have things like verbose, you have guessed, disk, changed, and stuff like that. Now, what we're trying to do here is with this last feature, fraction of dictionary word by size, we figure out what are all the different words that exist in a log, okay, that actually make sense in the English language. So we say, okay, you have a four-letter word, which is, let's say, disk. Does that exist? Yes. Then, and we have a five-letter word that exists. Does it exist? Then what is the percentage? What are the number of, how many out of the number of words, how many of them are five-letter words? How many words are actually four-letter words? And how many of them exist in the English language is what we use as a percentage to figure out what is the combination of the number of letters of words that exist for this specific log, which actually helps us. So we use that, and then we actually, so we use that basically to build our feature set. Now, even if we build our feature set, we are approaching the problem as a supervised problem. So what that means is that we need to be able to label the data. Okay, we need to be able to identify where these different logs are coming from, because we need to train the machine. And so the labeling is actually what forms the response of the model. And with that, so the way I did it is, because I have actually studied these these logs for many years, I know what source these logs are from. For example, if I see a token like this which says rsa.ims.authn, then I know it's from the system, which is like a secure ID. If I see something like an ASA, then I know it's from a Cisco ASA log. If I see something like an ACC, I know it's from Big IP or F5 networks. If I see something from sensor, it says air magnet. CPPM, it could be like an Aruba network. So these are different tokens that actually exist in the data. Using the experience, I know how to tag these tokens. So what I do is I tell another piece of code, which is not the machine learning algorithm itself, to tag these. Whenever you see these tokens, tag these as the response, is what I tell it. And that is actually available. Give me 1 second. Let's pull it up from a GitHub. Okay. For some reason it does not seem to be populated here. I think we missed it. I can quickly populate that for you right after we finish this call. So I have used that mechanism to actually create the labels for this data. Now, after we have created the labels, our data is basically going to look like this. Okay, so now this might look like a lot of baloney, but I'll tell you how it is. This 30 is basically the priority value that we extracted from a certain record. 5 is basically the format, the date format that we saw in that specific record. 138 is the number of characters. 2 is the number of IP addresses. 0 is the number of MAC addresses in that record. And when you see network.txt, it is basically the tag. In this case, it is the response column, which says that this log is coming from a network record. Okay, and what you see here is 0 0.4, 0 0.2, and 0 0.2. This 0 0.4 basically means 40% of the English language words in this line of log are 4-letter words. Then 20% are 5-letter words. Another 20% are 6-letter words, and this should be 7 and 8. Another 20% are actually 8-letter words. So that is how you read this out. And for another one, it is basically the same thing, where we say, okay, you have a source which is priority value, which is 166. Your date format is 4. Your the number of characters is 166 as well, and you have no IP addresses, no MAC addresses. This is basically from a VMware, and you have 5, 4, 5, 6, 7. There is one 7-letter word, and that's about it. So this is how your data would exist for your modeling. Now, without much further ado, let's see how we can get this data in. Okay, so now I'm running a basic cluster on my computer itself. It's exactly the same process to run a basic cluster so I'm running an H2O instance on my machine. This is a single instance machine. It's not a cluster. If you want to run a cluster, you instantiate it the same way. So let me show you how we do it here. So if you were to go to h2o.ai, okay, and what you say, download. And here you will choose, download the latest version. Okay, you click on this and you'll get a zip file. 175 MB. So if anyone is having network issues to download that, let us know. It's perfectly fine. Okay. So now that we have downloaded it, okay, now all we do is we basically unzip whatever we downloaded. Okay. Let's just check what we have. CD H2O, 3.10. So this is your folder. Okay, and you've got your Python library aspects, and you've got a H2O.jar, your bindings, and your R. Now all you do is you say java-jar, okay, H2O. And your entire setup is running. Okay, so now you already started running an instance of H2O. So when you start running this, you actually get something like this, which says, it gives you your IP address and it gives you a port which is 54321. Okay, H2O's default port is 54321. So just remember that. So now we can put this, IP address 172.155. Okay, and you can say, take me there, which is not very complicated. Okay, so now you've got your H2O instance running. Okay, so now, well, what can you do with this? Nothing much, right? So now you need to import your data. Okay, in this case, I am going to import the data that I just described, which is this. Which is basically this. It's converted every log system, every log record that we have, which is going to be something like this. Okay, every record that looks like this has been converted into a bunch of features that looks like this, with a label, so that the machine can learn, and then once the learning process has been done, it can identify what is the, what are the next, it can identify the logs and so on. So now we access that data. Okay, okay, so you choose whatever data set that you want, and then you say import. So now H2O is ready to, so H2O has imported your data set, and now it gives you an option to parse the data. So now you say parse the data. Okay, so now what happens is this. Hang on, let me see if I can move this out so that you guys can see much better. Okay, so now what you see here is it has parsed the data. H2O has automatically identified that the separator is actually a semicolon, and it says, so it's also able to identify that the first row does not contain a header, it contains merely a data set. So it's able to identify all this. Now you also know, so it lists all the columns that it can see in the data set. So this column is basically our priority value column. Now, although this is numeric, it is specifically factorial because we just have we have two or just a few values in this case. So you see 30, 166, 158 and such. So we change this to enumerate. Enumerate is basically factorial. Okay, and then the second one is basically the date format. So there are 5 different date formats that we have. So in this case, we change this to enumerate. Okay, and then the third field is basically the length of the number of characters in the log. This we keep it at numeric because it's originally a numerical value. And we also choose the number of IP addresses. The number of IP addresses too is going to be numeric, and the number of MAC addresses too is going to be numeric in this case. Okay. The reason is because these two are actually numerical values. They're not necessarily categorical identifiers. And this is a response column. The 6th column is going to be a response column, which we retain it to be at enum because it is our multi-class identifier. This is basically our multi-class identifier. Okay, and column 7 to 18 are all our 4-letter word to I think if I'm right, it should be 15-letter word identifier. Okay, we keep all of them as numeric because these are all basically decimals that we are looking at. We are basically looking at it as a percentage of we're looking at it as a percentage of the words that exist. So now what we do after we have done this entire process, we say parse. Okay. So as you can see, the parsing process is extremely quick. It's really fast for the it's really fast for the data to be parsed. So the data actually gets imported is in memory. It's not on disk, but your original data set can be can exist anywhere. It could be on disk, it could be in memory, wherever you think you can bring it out from. But this is when the H2O process is running, the data actually exists in memory. So now we have imported this data. Okay. So now what do we do next? Now we actually build the model. So before we build the model, let's just do a sanity check. Let's just see how things look. Okay. So we've seen here, we know, okay, the first column, which is basically our priority value. Oh, by the way, guys, I very sincerely apologize. By the time when I put this out on GitHub for you guys to try this out, I'll actually make sure that I have labeled the columns so that you know what each of these columns are. I tend to take it for granted because I know this data set really well, so I do not use columns, but I understand a lot of people might be seeing this for the first time. So I very sincerely apologize, and I hope you don't feel bad about that. So, so what we do here is that we do a sanity check. We'll check the fields. What we chose the fields are actually right. Priority value is enumerate. Our date type is also enumerate. Number of IP addresses. Number of characters, IP addresses, and MAC addresses are all integers in this case. Our multi-class response that we are choosing is also enumerate, and the rest of them are all real because it's decimal. So now we go ahead and we say build a model. Okay, so when you say build a model, this is where you're actually applying the machine learning algorithm, and this algorithm splits. This algorithm is the one that is used, which learns how the features exist and spits out a model. So when you say build a model, you get different kinds of options. You can do deep learning, random forest, gradient boosted machines, linear models, and some of the rest of them that exist are all unsupervised. So let us say let's for now choose GBM, which is gradient boosted machines. And one of the things that might be that a lot of advanced users might realize that GBMs know that GBMs are necessarily trying to reduce bias while they actually have low variance, while random forest actually has Sorry, while GBMs might have high bias and they're trying to reduce the variance, random forest usually has high variance and has low bias. So we choose this because our data is less noisy, so which is why we choose GBM to run this. So let's try and name this something. First H2O GBM model. Okay. Now, after you do this, what you do next is you set a training frame. So you could set a training frame like that. You could give it a training frame, and then you could also give it a testing frame. But now the thing is, to do a train and a testing frame, what you need to do before is you need to split the data. Because the idea of machine learning is that you split the data into 60-40 or 70-30, 75-25 or 80-20 or 90-10 or whatever breakdown you want, and you give a good chunk of data, which is the larger size of data, for the algorithm to learn what is in the data. Okay, you give the 80, the 70s, the 60s, 80s and 90s for the algorithm to learn how you are, and then using that learning process, then you predict on the rest of the data. The rest 10% or whatever you provide. So in this case, let's say you want to split the data. Okay, you say let's split this data by a ratio. Let's say 75-25. Okay, let's keep the same thing. Let's say create. Okay, so now we have new frames created. Frame 0.75 will be used for training, and frame 0.25 will be used for testing. So let us go back and first build using these two frames. Okay, so let's say gradient boosted machine again, and now first H2O GBM model. Okay, let's say 1, because who knows how many models we'll end up building. So let's say our training frame is 0.75, which means training frame means the amount, the data set, the part of your data set that you're giving to your algorithm to learn. And validation frame is the part of the data set that you are giving to your algorithm to verify that what it learned is correct or not. It's as simple as that. Okay? But now you also have to say, what is the response column? You have to say, what is your end target? In this case, our end target is the multi-classification, is the multiple types of classification of the sources of the logs, which happens to be column 6. Okay? And we are not necessarily ignoring any column. So let's say you wanted to ignore something. Let's say, for example, you have a hunch that the dates don't add much value. Okay, then you would say ignore date. You would click it that way. Okay, or you would say forget the priority value. We don't need that. Then you would choose this. Okay, in this case, we'll actually choose all of them. So now what we do is then we say how many number of trees it needs to build. So the number of trees are basically the different number of decision trees that are built based on the GBM model approach. Okay, and in this case we choose 50. I would actually like to reduce it to 25 in the interest of time, so that I can show you how this thing works, but not necessarily be so close to the accuracy that I look for. And max depth of 5 means that there could be 5 leaves in each tree. Okay, there could be 5 leaves in each tree. And minimum rows actually means that what is the minimum number of rows that are needed for a certain leaf to be valuable. For example, when a decision tree gets made, you could have a leaf that gets generated based on one data point. Now the problem is machine learning believes in the idea that more data means more validity of that kind of data. Okay, but if you have just one instance of a data, there is no validation of that kind of data. So that is why we say only if there are 10 rows of a certain kind, then you can use it for a certain leaf, is what we say. Okay, which is why we say minimum rows is set to 10. And the next one is basically we say n bins, where we use the numerical columns and that many number of bins to split the data. We also set the seed to -1 in this case. Learning rate is basically the rate at which the algorithm learns about your data, which we set it to 0.01. And you have to make sure that you set your learning rate to a low value so that your algorithm tends to learn slowly. Because if it tends to learn in larger jumps, then it might forget how the actual data exists. So it needs to learn a bit slowly. And basically, we also look at sample rate, column sample rate, and these are some things that I would actually leave it for you guys to look at, because I think we're kind of very close to our time. Okay, so let's set the rest of it very basic. I mean, let's set the rest of it into very defaults, where the fold column is basically telling us on what column do you want to fold the data on. Our offsets are offsets that you can set, weights that you can provide. So you can provide, for example, I think someone has just asked me saying, how would you handle class imbalance? Well, for class imbalance, the way you would do is you would provide weights for certain classes. That is something that you can set up here as well. But for that, you have to insert a column which specifies the weights. Now, these things I'll actually leave it to the defaults. Okay, the size of the confusion matrix, what is the hit ratio, and the number of bins, the stopping as well. So I'll leave all this to the default, and then I'll say build the model. Okay, and now the GBM model is actually being built. Okay, let's give it like a couple of minutes, and let's come back to that. Here, maybe this might be a quick time for someone to type in a question before that bar runs, like from here to here. Or maybe not. Okay.
Hey Ashrith, there's a question that popped up. It says the current demo instance of H2O, is it standalone or connected to Spark?
Oh, the current demo is actually is basically a standalone. We are running it on my local. I'm running it on my local machine. I think someone has a question of how H2O leverages GPUs. So the way we are leveraging GPUs right now is we are leveraging it through our deep water package, which interfaces with XGBoost, MXNet, Cafe, and through that we actually use the GPUs for running things in parallel. Okay, so we have the algorithm has actually run right now. So let's take a look at how the results are. Okay, so this is basically our scoring history that we have. Okay, and what we see is, very quickly we kind of converged to a very low log loss value. So, and based on the variable importance, we also see that the first one, which is the priority value, tends to have a lot more effect on the data, and the types of dates tends to have a lot more effect on the data as well. The number of IP addresses is the next one. The length of the number of characters is another one, and then C11, which due to my wrongdoing, I cannot figure out what is the number of characters in that. That probably is, I would like to say 6-letter words, and then probably 8-letter words, and so on. So that's how the importance is. So you see that this is a training matrix. Okay, let's look at how our results look like. So we see that, this is actually a training matrix where we see how many of the air magnet was trained into an air magnet and such. Okay. So you see our error rates are pretty good if you look at it. But let me take you to some of the cases where our errors are really bad. So if you see there is 1 in 6, this is pretty high when you say there is 1 in 6 or 2 in 15. Or 7 in 7, where the error rates are pretty high. And we have, 1 in 2. Now, out of 150 records, we have like 690 records that are actually wrong, which is kind of okay. And the next one that we look at is basically our validation matrix, okay? Here, what we see is we see that the error rates are pretty bad as well in some instances, where it's like 2 out of 21, 2 out of 20, 1 out of 155, 1 out of 161 is okay, 2 out of 6, 1 out of 1, and 1 out of 5. Now, what you need to see in this is that I think someone had very specifically asked a question about class imbalance, and that is exactly the problem here. So there are some of them, if you have enough data, then the validation is really good. The system understands that that is a certain that belongs to a certain family of data, and the training and the validation happens to be really nice. But if the data set is really small, for that matter, like these really small values, okay, then it doesn't necessarily be that good. So in that case, what we need to have is we need to have some kind of a penalization or a weighted setup where we are able to better identify the data set. Okay, so for that, you'll actually have to tune the data and see how you can fix on it. So this is basically our output, and I'll quickly take you through how, let's say you want to implement this code, okay? Maybe some of the people in our audience are actually from the DevOps group who want to take this code and implement it, with their syslogs and see how things work. So for that, you say preview Pojo, and you actually get a Java class. This is the entire Java class of our algorithm, okay? All you have to do is you have to write a wrapper class which takes your logs, okay, and feeds it into this algorithm, okay, and then this algorithm will spit out the multi-classification that you need. It's as simple as that, okay. So now, having gone through this, let me stop here with the presentation and let's see if we have any other questions. Yeah, let's quickly switch to questions and see if there are any questions that we can do.
Great, we have a bunch in the chat questions window, and I'll just slowly go through them. Let's see here.
I think someone had a quick, 20% so we did not take 2-letter words because, they tend to be very common, so we started off from 4-letter words. Yes, the way we have actually implemented, I think someone's question is, can such a use case be used for real-time security performance monitoring using log analysis? Yes. The algorithm that the design I'm basically showing you is a very simple implementation. This is just to take you through how the process is. We actually have implemented an ensemble of this, basically meaning multiple of these kinds of algorithms in an ensemble, basically like a heterogeneous grouping. And there is a weighted decision from each of these classes that we take to identify each of the log sources. I think there are repeatedly people who have asked us to share the Git repo. We will definitely share the Git repo. If you've signed up for this on Meetup or through GoToWebinar, you will get an email for the GitHub. I'll assure you on that, okay? How do you derive the numbers and the actual data? Vaishali Katkar, if you can, maybe send us in detail about your question, we'll be able to answer. Okay, we can just join. Say something. You're going to make this available for download. Yes, Ian, I think a lot of people probably missed the talk, so they want to know if this is going to be available for download or to listen later. I'm guessing we can help them out.
Yep, it's being recorded, so it'll be posted on our YouTube channel as well as a recording sent to the attendees and those that missed it. And
Okay.
here's another one that popped up, Ashrith. Why do you use GBM instead of RF or deep learning?
Super question. I think one of the reasons we use GBM in this case is because, as I said earlier, this data is less noisy. Let's say we were going through a lot of noisy data. There were a lot of other kinds of data that was coming into the system that we could not classify at all. Then I would probably go with a random forest model, which would be much better. A deep learning model could be used, but it is better to run a decision tree model, which is kind of quick and short for us to identify, which is why you usually tend to do deep learning, a tree-based model first and then jump to a deep learning model. Someone had a code which says for Python as well. Yes, you can write a wrapper around the same Java, run the jar. It's perfectly workable.
Can
Thanks.
we add our own algorithms to H2O?
I'm sorry, Ian, can you say that again?
Sure, said, can we add our own algorithms to H2O?
Not at this point. You could make so I'm guessing you might want to like make your own ensemble and things like that. If you want to make it, you can make it outside, but you'll have to work with the Pojo. So you can't add algorithms to H2O right now. But you can definitely contribute to the H2O itself, which is an open source and which is purely available on our GitHub. Um, so if you were to go, to H2O, you can actually see H2Os right here. I'm guessing you guys can still see it. So you are more than welcome to contribute it to here. But if you just wanted to add it to yourselves, of course, you'll have to do it on your own version of it. So I think I probably have to take back my words. Yes, I think you can add it if you are willing to contribute. Yeah.
Awesome. We have time for two more questions we'll answer.
Sure.
Would you or would you not consider this data to be noisy data?
Actually, this data is not noisy because the reason why I would say that is with my vast amount of experience with security and networks, it's kind of easy for me to identify this data. And I know, and I'm able to very intuitively identify, if the data is noisy or not. At least this data that we're working with is not that noisy. I've seen data that actually comes with a lot of funny characters which do not make any sense in log data. That I would say is a lot more noisy in identification.
Awesome. And here's the last question. H2O deep learning supports both image processing problems as well as NLP.
So for the NLP, we'll have to go through the word-to-vec process that we have right now. We actually have example implementations that you can take a look at online and see how this can be used. But we definitely have a CNN implementation that you can use for image classification.
Awesome. Well, thanks everybody for your time. We're a little bit over, so thanks for hanging in there with us. Again, as we mentioned, the slides and recording will be available. Just give us about 24 hours to post and send to everybody that attended and not attended. If you haven't already, go ahead and download H2O. Special thanks to Ashrith for presenting today, and that's it. Thanks, everybody.
Thanks, guys. Really appreciate the fact that you guys were there and patiently listen to the whole thing. Thank you.
Have a good day.
Take care.